All right, we're going to continue with section 14.2 in this video, and we are on page 921. We are going to do number 24, which says, well, the directions say in exercises 22 through 29, change the integral to an iterated integral in polar coordinates and then evaluate it. So for 24, we are given the double integral from 3 over root 2 to 3, or the iterated integral actually, and then from 0 up to the square root of 9 minus x squared of 1 over the square root of x squared plus y squared dy dx. All right, so our first order of business whenever we're being told to convert an integral that we're already given is to sketch the region that we have. So we have y goes from, well, first off, they're telling us in the directions to change the polar coordinates. The reason being is that we would probably run into some difficulties if we were to try to evaluate this integral as is in rectangular coordinates. So we're going to switch to polar coordinates, which should hopefully make our evaluation much easier. But first, let's sketch the region that we're considering in terms of these rectangular coordinates, and then we're going to convert to polar coordinates. So we have y goes from 0 up to y equals 0 up to y equals the square root of 9 minus x squared. So y equals the square root of 9 minus x squared. That is, of course, y is greater than 0, and it's going to be a semicircle with radius 3 centered at the origin. So we'll start with that. All right, so we have our semicircle. Oops. We're almost with a semicircle. Let's try it one more time. Yeah, that's good enough. All right, so now our radius here is 3. So we'll label that there. And we're going from 0. So we're right now, the way this is, we're going from function to function in the y direction. So we could indicate our arrows here, but we're going to switch to polar coordinates anyway. So there's no need to indicate whether we're doing a type 1 or type 2 region. Then our x goes from 3 over root 2 up to 3, and we already have the 3 there. So we'll put x equals 3 over root 2 right there. So let's put, so our region is this region right there. All right, so that's the region over which we're integrating, and we need to change that region to polar coordinates. Now, I'll also write down what we had in rectangular coordinates, that x was greater than or equal to 3 over root 2, and less than or equal to 3, and y was greater than or equal to 0, and less than or equal to 9 minus x squared. So keeping in mind we're switching polar, we know we need to figure out what do r and theta vary between instead. And some of it we can see that our top bound for what theta varies from 0 down here on the x-axis up to whatever this theta is, where this dotted line meets the semicircle. So we have to figure out what that theta is. We can't see that from the picture. And then we see that our r varies from something, this dotted line, there are a bunch of different r's on that dotted line, out to 3. Because remember, r is your distance from the origin. So r is never equal to 0 because we don't have anything in this region right here. So r is always going to be something that's past this dotted line, and it's going to top out at 3. So we can tell our lower bound on theta is 0 and our upper bound on r is 3. But we're going to go through the details of each aspect of this. So what we'll use is each thing that we see here. We see x equals, well, we won't use all of them actually. We see x equals 3 over square root of 2. We're going to use that and convert it to polar. We see x equals 3. We'll use that and convert it to polar. And we see y equals 0. We already discussed that one. That one gives us our theta equals 0. And then y equals the square root of 9 minus x squared. So we'll use each one of those things. So I'm going to start with the y equals the square root of 9 minus x squared and convert that to polar. And I'm going to do it two ways. You can convert at whatever stage you want to in your algebra. I tend to do it earlier only because the only reason I do it earlier is because we don't tend to be as accustomed to working with polar coordinates, and the earlier I do it, the more accustomed we can get to working with polar coordinates. So over here, I'm just going to do the same thing twice, just do it two separate ways. You choose whichever algebraic approach you would prefer. It doesn't really matter. So y in polar coordinates is r sine theta equals the square root of 9 minus x squared, which is r squared cosine squared theta. Then we square both sides here, and we end up with r squared sine squared theta equals 9 minus r squared cosine squared theta. And if we move the r squared cosine squared theta term over to the left, we have r squared cosine squared theta plus r squared sine squared theta equals 9. We use our favorite trig identity. It tells us the left-hand side of this is just r squared equals 9. And then remember, r always has to be greater than or equal to 0. So this tells us r equals 3. All right, so now we saw that bound from our picture, but this is how you go through it algebraically. And now let's do it by switching. So I switched to polar coordinates in my first step. Here, I'll wait until later to switch to polar coordinates. And this is just the same as y squared equals 9 minus x squared, which is the same as x squared plus y squared equals 9. With x squared plus y squared, now if we switch to polar coordinates, that is r squared equals 9, or r equals 3. So either approach is fine. And we had already seen this information from the fact that we saw our upper bound on y was the square root of 9 minus x squared. So now the next thing is we'll look at using these x values. So we already used y equals the square root of 9 minus x squared to get an r. It didn't do us that much good because the more difficult r, we haven't gotten that yet. So actually, let's do that next. That's probably a better order in which to do things, is to see what we get. So we have that. Let's do a little separation here. Next thing we'll do is we'll look at what we get from, the x's. So we have x equals 3 over the square root of 2. See what information we can glean from that, as well as what we get from x equals 3. So x equals 3 over the square root of 2. X, remember, is r cosine theta equals 3 over the square root of 2. So now there are two things here, r and theta. We could be trying to solve for, figure what our bounds are for theta, or figure out what r is, and we're actually going to use this equation for both of them. At this point, let's use it to figure out our other r, since we already have one of the r's. So now to do that, that means that we're just taking this and we're solving this for r. So this gives us r equals, and let's look at our picture so we make sure we know what we're doing here. So x is equal to 3 over the square root of 2 is what I'm looking at right now. And I'm trying to solve for r. Now let's reason through why we would use this to solve for r and how this relates to our picture. So our R is, and I'm going to just draw some different starting points for the radius. So these are my lowest bound. So whatever angle this is, my radius goes from this point where my cursor is all the way out to 3. And whatever angle this is, my radius goes from this point out here all the way out to 3. So these lines you see me drawing here are the lower bound on the radius at each one of these different angles of theta that I'm changing. So for this top one, for instance, I know my angle, whatever it is, my radius just goes from 3 to 3. Whereas on this one, I don't know what number that is. I have no idea. But my radius goes from that number all the way out to 3. At this angle of theta, my radius goes from whatever this number, when I say number, I mean what length of r this is, this length r, all the way out to 3. So we can see that our radius is indeed a function of theta. And what we're trying to figure out is, what is our radius when we're on this line, x equals 3 over root 2. We can see what the radius is clearly when we're on the circle, but what is the radius going to be when we're on that line? Because it's going to vary depending upon what theta is. So that's why it's reasonable that we have here our r is going to be a function of theta. So we end up with 1 over cosine theta times 3 root 2. And cosine theta is just secant theta. So we end up with 3 over root 2 times secant of theta. So now we have our bounds for r, and let's deal with this later. So we have our bounds for r. R varies between, so what is our lower bound for r and what is our upper bound for r? The outer part of the circle is 3, so that's our upper bound for r. And our lower bound for r is that line, x equals 3 over root 2, but that is the same as r equals 3 over root 2 times secant of theta. So 3 over root 2 times secant of theta. So now we have our bounds for r. So next we can go and deal with theta now. And one aspect of theta we already know. When we're on the y-axis, our theta is 0, and then it goes all the way up to theta equals whatever this is when we're at x equals 3 over root 2. So we had r equals 3, and then we had r equals 3 over root 2 secant theta. So we're done with that. Now let's look at x equals 3 over root 2 again, because we just looked at this. Will also tell us something about our theta. So this is the same as r cosine theta equals 3 over root 2. And now this time we're trying to solve for theta. So we're going to isolate cosine theta. Cosine theta equals 3 over r times the square root of 2. So now our theta, we certainly don't, we want bounds on theta, so we already know that r is a function of theta. We can't write theta as a function of r as well. We know that we can only go from function to function on one of our variables. So r is already going from function to function, which means theta absolutely, of course, has to go from constant to constant as it usually does. So now, but we have an r in here right now. So how are we going to deal with that? When x equals 3 over root 2, what we're looking at is we have, when x is 3 over root 2, we can look at that top point if we want to up there, and that very top point for x equals 3 over root 2, we know that r at that point is 3, and that's this point right here is the point that we're trying to figure out, because we already know theta is equal to 0 down here on the x-axis. We need to figure out what is theta when we go all the way up to this top line right here. And on that top line, we know that r is equal to 3, and it's not equal to anything else. It's always equal to 3. So this tells us, since when x is equal to 3 over root 2, r is equal to 3, we can just plug in 3 there. So cosine theta equals 3 over 3 times root 2, which is just 1 over root 2, which tells us that our theta is equal to pi over 4. All right, and again, from our picture, we can already see that the other bound for theta is 0, but we'll just go through and do the math for it as well. It's going to come from the fact when x is equal to 3, which is what we had. So that's r cosine theta equals 3, or cosine theta equals 3 over r. And let's look and see what should we be looking at for our r here. So again, when we're looking at x is equal to 3, so our x, we're at this point right here. We're looking at x equals 3. And what is our r at that particular point? Our r is 3. So that's why we plug in 3 right there. So this is cosine theta. Cosine theta equals 3 over 3, which equals 1, which tells us that our theta is equal to 0. And now we have our bounds for theta. So theta goes from 0 to pi over 4. All right, so now we can go ahead and write down our polar region R. R is equal to the set of points r comma theta, such that theta goes from 0 to pi over 4, and r goes from, our lower bound on r was 3 over root 2 times secant of theta, then up to 3. So now with that information, we can go ahead and set up our integral in polar coordinates. So we now have polar integral. Theta goes from 0 to pi over 4, and r goes from 3 over root 2 over root 2 times secant of theta, and then up to 3. Our integrand was, where's the problem? 1 over the square root of x squared plus y squared. So we want to make sure we get rid of our x's and y's in the integrand. So the square root of x squared plus y squared is just the square root of r squared, or just r. So 1 over r. And we've taken an integral and changed it to polar coordinates. So we need r there. And then these are r's here. So that's dr. And then theta's d theta. And then you would, of course, evaluate that integral at that point. So we will stop this video here and then continue with conclude section 14.2 in the next video.